Today we're going to be talking about one of the most important but sometimes confusing topics in Intro to Probability and Statistics courses called Bayes' rule. Bayes' rule, though, really just builds up on two fundamental ideas of conditional probability. The first being that the probability of an event A occurring given that an event B occurred is just the probability of A and B occurring over the probability of B occurring. So here I introduce some notation, so let me just quickly go over that. This slash sign right here basically just means A given B. And this upside down U basically just means A and B. Now, what do I mean by A and B? These are just events. One example of an event is just tossing a coin and getting heads. Now, the next thing you have to know in conditional probability is that if we have two events A and B occurring at the same time, and B depends on A, then this is just equal to the probability of A occurring times the probability of B given A. And with these two ideas, we'll build up Bayes' rule. Now, this might seem a little abstract right now, but it'll make more sense when we look at an example. Now let's look at a classic Bayes' rule problem. Imagine that you have a coin. It's either fair or it's biased, and if it's fair, the probability of getting heads is 1/2, and if it's biased, the probability of getting heads is 2/3. Now, out of all the coins in the world, the probability of getting a fair coin is 1/4. Now, imagine the following scenario. Imagine that you toss a coin and you get heads. Now you're asked, what's the probability this coin was fair? So this seems a little weird because there doesn't seem to be any correlation between these two. But with the beauty of Bayes' rule, we will be able to figure out exactly this. So, before we get started, let's formalize this problem a little, because it is a little weird. So, there are two main events going on. The first being whether the coin was fair or biased. So, I'm going to label that as fair. And the second being whether the coin we flipped was heads or tails. So, I'll just say this as heads. Now, what we have to do now is, based on these events, let's define our probabilities. Well, the first one that's pretty easy is what's the probability that it was fair? That's just straight up 1/4, right? Now, the next two, how do we use these two probabilities right here? That's a big question. Well, this probability occurs when the coin was fair. And hey, that means we have a conditional probability. Only under the condition of fairness of the coin do we have a probability of getting heads of 1/2. So what does that mean? That just means that the probability of B, given that we got a fair coin, is equal to 1/2. And then now, the other probability that we have is that the probability of getting a heads when it's a biased coin, that's the probability of B, given that we got a biased coin, so I'm going to label that as just not A, having a slash above it, is equal to 2/3. So these are our main probabilities right here. Now, what's the question asking? The question is asking, what is the probability that the coin was fair if we got heads? Hey, that's another conditional probability. That's just the probability that the coin was fair given that we tossed the heads. So this is a big question. So the first step is remember our conditional probability rules. This is just a matter of defining the conditional probability as the probability of A and B over the probability of B. Now, notice that this probability of A and B are dependent events, right? Because whether we get heads depends on whether it's a fair or biased coin. So this right here can be further split up into, using our conditional probability rules we talked about earlier, as the probability of A times the probability of B given A over the probability of B. Okay, seems like we're getting somewhere. Now, what is the probability of B? That seems like a big question right now. Well, the probability of B can be split up into two cases really. Either the coin is fair or it's biased, right? Because only then, we have to first figure out whether it's a fair or biased coin before we can figure out the probability that we get heads. So, what you have to realize is that getting a head, first you either have a fair coin, so you have to first have a fair coin and get heads, or you have to have a biased coin and get heads. So these are our two basic probabilities that we have. And notice that choices that we have based on whether we get a fair or biased coin, the heads when it's fair and the heads when it's biased, those encompass all the possible events that we can get heads. So what you have to realize is that we just have to add these two probabilities to get the probability of B. Now, what you have to notice also is, hey, this is another conditional probability rule. This is just the probability of A times the probability of B given A. And now this right here is just the probability of not getting A, or being biased, times the probability of getting heads when it's biased. So now let's take a moment to just digest this thing. So we basically have the probability that we got a fair coin and we got heads, plus the probability that we got a biased coin and we got heads. And that encompasses the probability that we got heads. And that makes sense intuitively. So now here, we can substitute this in here, this as probability B, and we'll get our formalization of Bayes' rule. And congratulations, you just derived Bayes' rule. And now we can plug in our probabilities and we get 1/4 times 1/2 over 1/4 times 1/2 plus 3/4 times 2/3. And that gives us a probability that the coin was fair given that we got heads of 1/5. And this makes sense because if we got heads, it leads us to believe that we had a biased coin in the first place. So the probability that the coin was fair is not very likely. Now let's take a visual perspective of exactly what's happening with Bayes' rule. Bayes' rule at the end of the day is all about making decisions. Either we can have a fair coin or we can have a biased coin. That's our first decision. The probability of getting a fair coin is 1/4. The probability of getting a biased coin is 3/4. Now once we have a fair coin, we can make one more decision. The coin can either end up as heads or tails. Now it happens with a fair coin that's equal. So that's just 1/2 and 1/2. Now with the biased coin though, the probability that we get heads is 2/3 and the probability that we got tails is 1/3. Now, what if someone asks you what's the probability of getting a fair coin and getting heads? That's just 1/4 times 1/2, and that's equal to 1/8. And we can do this for all the probabilities and multiply them out, and we'll get basically our events. So this is 1/2, and this is 1/4. And notice that all these events add up to 1, so that makes sense. Now, what is the problem asking us to do now? It's asking, what is the probability that the coin was fair given that we got heads? Hey, what are the only events where we got heads? Well, hey, that's this event right here, and this event right here. Those are the only cases where we got heads. Now, it's then asking what's the probability that the coin was fair. The only case in which the coin was fair was right here, because that corresponds to this branch. So our final probability is just 1/8 over 1/8 plus 1/2, and that gives us 1/5. So this is the visual perspective of Bayes' rule. We can also look at Bayes' rule from a geometric perspective, where we're basically going to have the square that represents all the coins, and we know 1/4 of that square is going to be reserved for fair coins. And we know 3/4 of that square is then going to be for biased coins. And within the fair coins, we know only 1/2 of the fair coins end up being heads. And 2/3 of the biased coins are going to end up being heads. So we're looking at heads because that's our condition in this probability problem. And what we're looking for is the probability that the coin was fair given that it was heads. So that's this region right here. And what Bayes' rule asks for is this region over this entire shaded blue region. And that's a geometric perspective of Bayes' rule. At some point in this video, you might have asked yourself, hey, who cares about Bayes' rule? In other words, when am I ever going to use it? Well, it turns out that Bayes' rule is used so often in predicting events based on real-world statistics. Let me give you an example. Imagine that you're a doctor, and you realize that 30% of your patients end up having the flu, and 70% have something else. And you know that of the flu patients, 90% develop a fever. And of the patients with something else, only 20% end up with a fever. Now imagine now that a patient walks in with a fever. What is the probability that he has the flu? And this is a classic Bayes' rule type of problem in disease prediction. Another cool application of Bayes' rule is figuring out how to reverse a conditional probability. Imagine that your friend and you are having a debate about whether money buys happiness, and your friend states the following statistic: 20% of happy people are rich. And then you think about this for a little, and you realize, wouldn't it make more sense if I knew how much percent of the population that was rich also ended up being happy? So now you do some research and you realize that only 5% of the world is rich and 30% of the world is happy. But now you have a Bayes' rule problem, and you can figure out exactly what percent of rich people are happy, and you figure out whether money buys happiness. And this is just the start of what you can do with Bayes' rule. I hope you enjoyed this video on Bayes' rule. Thanks for watching.